Hi, my name is Benjamin Bowman, and today I'm going to present our work on detecting lateral movement in enterprise computer networks with unsupervised graph AI. This work was done in collaboration with Craig Laprade, Yu Deji, and Howie Huang at the George Washington University. This talk will consist of 5 sections. In the first section, I will discuss lateral movement and the life cycle of a cyber attack. In the second, I will talk about applying machine learning to graph-structured data and what we mean by unsupervised graph AI. In the third section, I will show how we apply our graph machine learning to the problem of lateral movement detection. And in the fourth section, I will discuss our evaluation and results. In the fifth, I will conclude. So let's get started with lateral movement and the life cycle of a cyber attack. Advanced Persistent Threats, or APTs, are stealthy and sophisticated threat actors that are typically state-sponsored organizations. Attacks waged by APTs are complex, multi-stage campaigns that can span weeks to months to even years. This is the caliber of cyber attack that we are considering in this work. The figure on the right is a simplified version of the cyber kill chain, showing the various key stages of a cyber attack by an APT-level adversary. An attack typically starts from some initial compromise, typically on a low-privileged system, as these systems are usually manned by less technical personnel who are more vulnerable to the most common and effective techniques for compromising credentials, such as phishing scams, credential stuffing, or even just using bad passwords. After establishing a foothold inside the enterprise network, an adversary begins the cyclic process of lateral movement in order to gain privileges and access to the accounts and systems necessary to accomplish their mission. This cycle typically is composed of steps such as reconnaissance in order to identify what machines and services an adversary currently has access to, privilege escalation either on the local machine or by moving laterally to a new system on which the compromised account has higher privileges, and credential harvesting from either memory or even just files on a compromised system. And finally, the end of the campaign is typically referred to as actions on objectives, which can mean many different things. In the figure, we show domain admin compromise as the end of the campaign, which is synonymous with total network ownership, as the domain admin will have the privileges to perform basically any action on computers in the domain. However, actions on objectives could be many other things, such as data exfiltration, data destruction, installing ransomware, or others. So, lateral movement then is the key stage of the attack lifecycle that allows the adversary to ultimately achieve their actions on objectives. And this is a really very challenging thing to detect, as APT-level adversaries often rely on using legitimate credentials, services, and authentication channels to move throughout the environment. For example, Windows offers many legitimate services such as WMI, WinRM, RDP, SMB, and others that an adversary can use to move laterally through the network. This means the traditional signature-based mechanisms for identifying compromised systems based on malware and exploitation will be totally ineffective here. What we really need is a technique capable of learning from past authentication behavior that will allow us to detect future anomalous authentication events that may be indicative of lateral movement. Now, in order to explain how we do this, let's first take a step back and talk a little bit about how we can apply machine learning to graph-structured data. Graph data structures are characterized by a set of nodes and edges and have proven to be an extremely powerful way to represent heterogeneous relational data, such as social networks, computer networks, knowledge graphs, and others. However, applying machine learning to graphs is non-trivial due to the non-Euclidean nature of the data. So what do I mean by that? Well, if we look at the figures on the bottom, we can see on the left a hand-drawn digit 8 from the well-known MNIST image classification library, and on the right, a visualization of the well-known Zachary's Karate Club social network. We can see that for the image of the 8, the location of the individual data points, which in this case are pixels, and the order in which they appear is of very high importance. If we were to rearrange the pixels, the image would certainly change as well, and if we change enough, the image would likely no longer be considered the digit 8. On the other hand, with graph-structured data, there's typically no notion of location or order. If you were to arbitrarily rearrange all the nodes in the graph here, it would still be the same graph, just visualized in a different way. Also, there are typically no such thing as a first node or a last node in graph structured data. This means that most machine learning algorithms do not work out of the box on graph structured data. So what do we do about this? Well, it turns out graphs can be sampled by random walks, and the resulting sequences of nodes are much more amenable to some existing data mining techniques, such as those from sequence-based domains such as natural language processing. This approach was popularized by works such as DeepWalk and NodeDevec. The figure at the bottom walks through an example of how this could work. An input graph is first sampled via random walks to generate a set of fixed-length node sequences. These node sequences can then be used to train a per-node embedding vector using a technique such as the continuous bag of words embedding process. In this process, vector embeddings are tuned for each entity such that they are best able to predict a node based on the context in which it is found. The end result of this process is a set of numeric vector embeddings per node in the graph, which captures important information from the graph structure. These embeddings can then be used in further downstream processing. So it is this process where we take a graph and learn meaningful node embeddings that capture critical relationships between elements in the graph that we refer to as graph AI. Now we will explain how we apply this technology to detecting lateral movement in enterprise computer networks. This diagram shows the full algorithm pipeline consisting of two distinct stages, the offline training stage and the online detection stage. During the offline training stage, we parse authentication log data, build an authentication graph, perform unsupervised graph learning, and train a link predictor based on the node embeddings and the observed authentication events. During the online detection stage, we monitor for new authentication events and predict the likelihood of the observed authentication events with our trained link predictor based on the learned node embeddings, and escalate an authentication event to a security analyst if it has a sufficiently low probability. Now we will go into further detail for each of these stages. In order to build our authentication graph, we parse industry standard authentication logs. In this work, we focus primarily on the Kerberos authentication protocol, as it is widely used and can be observed entirely from the network, not requiring host logging, which can be burdensome in larger enterprises. However, this technique can be easily adaptable to almost any authentication log, such as NTLM logs. Specifically, we extract the fields for client and service principals, which are essentially the unique IDs of the authenticating entities, as well as the IP addresses. Intuitively, this provides us the information on who is authenticating to what and from where. The figure on the right shows an example of a very simple authentication graph containing clients and principals for several users and services. There are two organizational units, the HR unit highlighted in yellow and the R&D unit highlighted in blue. The user Sally is clearly the administrator for the network, as she has authentication activity to services across both organizational units as well as the domain controller. Next, we perform node embedding on our authentication graph. This embedding process is the same as discussed previously and is based on the NodeDevec algorithm. We generate random walk sequences and perform continuous bag of words embedding. The figure on the right is the two-dimensional embedding space generated from the graph on the previous slide. We can see that the node embedding captured some very relevant information from the graph, allowing for us to distinguish between, for example, user machines and servers, organizational units, admins versus non-admins, and others. The final step of our training stage is to train a link predictor. This provides us the ability to, for any pair of node embeddings, generate a probability as to whether or not we should expect them to have a link in our authentication graph, or in other words, to authenticate to one another. In order to do this, we train a logistic regression classifier based on real edges from the authentication graph, as well as fake edges, in other words, authentication events that were not observed during the training. In the figure, we can see we take the node embedding for one of the HR users and the HR hosts that they authenticated to, take the Hadamard product, or the element-wise multiplication of the respective embeddings, and train our logistic regression classifier to predict that this authentication event has a high probability of occurring. Similarly, we take an authentication event that did not occur, such as an HR user node and an R&D host node, and label that with a 0 such that our logistic regression classifier will learn to predict that these types of authentications should not occur. Finally, performing online detection is a really pretty straightforward process. For any new authentication event, we look up the node embeddings for the two authenticating entities, pass them through our trained logistic regression link predictor, which outputs a value between 0 and 1, which we can interpret as the probability that the observed authentication should occur. We can then define a simple user-defined threshold delta, and if the probability of the link is less than this threshold delta, we generate an alert for the authentication event and forward it to a security analyst. Next, we will talk about how we evaluate our technique and the results. We applied this technique to two separate data sets. The Pico domain dataset is a custom dataset we built in-house and is currently available for use on GitHub. This dataset is characterized by a small domain, but with full visibility into a realistic cyber attack that spans the kill chain. The second dataset we used is from the Los Alamos National Labs and is the LANL 2015 dataset, which is from a real-world large-scale enterprise network. This dataset is characterized by its very large scale, but highly anonymized data with little to no details on the actual events of the malicious activity. The table at the bottom provides high-level statistics for each dataset. The difference in scale is very evident here, with LANL having over 1 billion total records compared to less than 5,000 in Pico domain. Similarly, the Pico domain has less than 100 unique user accounts, machine accounts, and computers combined, compared to over 100,000 in LANL. In total, we tested 6 different techniques for detecting the labeled malicious authentication events. We tested 2 different graph learning techniques with a varying context window. The graph learning with local view has a small context window size, meaning the embedding process only considers context nodes within a small distance of the target node. Differently, the graph learning with global view has a larger context window, which means the node embedding process will consider nodes that occur in farther reaching areas of the graph. We tested 2 more traditional non-graph machine learning techniques based on one-hot encoded authentication vectors generated per entity: local outlier factor and isolation forest. The local outlier factor is a density-based anomaly detector which finds outliers based on their localized neighborhoods, and the isolation forest is a decision tree style algorithm that identifies anomalies as those samples that can be isolated from the rest of the data set with a minimum number of splits. Finally, we tested 2 rule-based techniques, which are likely to be the closest to the techniques that are currently employed by cyber defenders for detecting malicious authentication activity. The unknown authentication technique identifies any authentication event that was not previously observed during the training period as anomalous, and the failed authentication technique detects any failed authentication activity. These are the results when applying all of the algorithms to the Pico domain dataset. We can see that, at least on this extremely small scale dataset, the unknown authentication detector was able to detect all of the malicious activity, however with a 1.5% false positive rate. The malicious activity in this dataset did not involve any brute force password guessing attempts, and thus the failed login detector only identified a single true positive, which was likely the result of human error during the attack campaign. We can see that the traditional machine learning techniques were able to detect some of the activity, but generated a significant amount of false positives. Finally, we can see that the graph learning approaches were able to provide an 80% true positive rate while generating no false positives. Note that the local view and global view had no change in performance. This again is likely due to the fact that the graph structure was so small in this experiment that both the local view and global view had a large enough context window to consider all nodes in the graph during the embedding process. These are the results when applying the same techniques to the LANL dataset. We can immediately see the effect of the real-world scale on these techniques, as the number of false positives are significantly higher than in the previous synthetic dataset. We can again see that the unknown authentication detector is able to capture a large amount of the malicious activity. However, in a real-world environment, this type of detector is far too noisy as it generates a significant number of false positives. This means that simply identifying new authentication events is not a practical technique to detecting lateral movement in a real network. The failed login detector, again, does not identify many malicious events, indicating that this attack campaign likely did not include a large amount of brute force password guessing attempts. The traditional machine learning techniques, again, are unable to identify a large amount of the red team activity, and they also fail to differentiate between the malicious and benign activity. This shows that the point-to-point authentication data alone, without the context of the underlying graph structure, is not sufficient for lateral movement detection. Intuitively, this makes sense since the simple point-to-point authentication events do not provide any information on the distance between entities that are authenticating. The authentication graph structure, however, does capture this information in the form of the number of hops between entities, which will be captured in the node embeddings. Finally, we can see that the best performing algorithm is the graph learning with global view, which achieved an 85% true positive rate at only a 0.9% false positive rate. We can see that the increased context window size of the global view detector provided a significant improvement over the local view detector due to the large scale of this graph. The local view detector performed slightly worse than unknown authentication in terms of true positive rate, but returned nearly 1/4 as many false positives. So it's clear that the graph learning techniques are capable of identifying more of the malicious activity while returning less false positives than the comparison techniques. However, it's important to note here that we still generated over 100,000 false positives. And as we know, false positives are really a serious problem in cyber right now because they waste a lot of time and they can even mask some truly bad events due to the sheer volume of false positives being generated by modern defensive techniques. So next, we set out to understand why these false positives were being generated and what we can do to help reduce those numbers. To that end, we made 3 key observations on the Lateral dataset. First, we noticed how many of the malicious events the extremely simple unknown authentication algorithm was able to detect. The vast majority of malicious authentication events in both of our datasets were in fact first authentication events. The second observation is that in the Lateral dataset specifically, all labeled malicious events are tied to specifically user-based authentications. And third, the malicious events are predominantly associated with only a few specific user accounts and systems. This intuitively makes sense, as an adversary will typically start with only a single or maybe a few initial footholds in a network, and they will be required to use those initial footholds to increase their presence. So you would expect to see the majority of anomalous events originating from only a few related accounts and systems that the attacker has compromised. So, based on these observations, we built several post-processing filters in an effort to reduce the number of false positives generated by our algorithm. The first results labeled as original are the baseline results on the Lateral dataset as presented previously, showing 100% of the original true positives and 100% of the original false positives. The known authentication filter is based on the first observation and will filter out any anomalies associated with authentication events that were seen during the training period. We can see that applying this filter reduces false positives by 10%, while only reducing true positives by less than 1%. The user-only filter is based on the second observation and will disregard anomalies that don't involve a user account. This reduces false positives by 20% while losing no true positives. The anomaly chain filter will drop any anomaly singleton, that is, an anomalous authentication event that does not share an entity with any other anomalous event. This filter also reduces false positives by nearly 20% while losing no true positives. Finally, when combining all of these simple filters together, we are able to reduce false positives by nearly 40% while only losing less than 1% of true positives. So the point here is to show that through some very simple post-processing filters, we can significantly reduce the false positives of this algorithm. So finally, to conclude this talk, Today we talked about lateral movement and how it is a critical stage of an APT cyber attack campaign and how it is very challenging to detect due to the usage of legitimate credentials and authentication channels. We talked about how to build an authentication graph using industry standard authentication logs and how to apply unsupervised graph AI in order to learn patterns of authentication activity between different classes of users, services, and systems, and ultimately identify anomalous authentication links with a link predictor trained on node embeddings. We showed how we were able to use this technique to identify malicious authentication events in 2 cybersecurity datasets with improved accuracy over several baseline methods. And finally, we showed how, through some simple post-processing filters, we can further reduce the number of false positives returned by our algorithm by nearly 40%. And that wraps up my presentation. Thanks for listening, and feel free to reach out to me with any comments or questions. Thanks.